Cheyenne here. Today I'm going to talk about another topic in strength of materials, namely the method of superposition in deflection analysis. So let's see what the question is asking us to find. So the question is asking determine the deflections and rotations at points A, C, and E for the beam it's given, and EI is constant. And we have a pin here, we have a roller, and E is the midpoint between point D and point F. So first thing, for following this question in this solution of this problem, it's really good to have a superposition table available, and so that you can see where we're getting the values that we're getting for basically the values of deflection and rotation. So let's start. The first step for the method of superposition always is to divide our cases to different cases and then add them together, right? So that's basically the definition of the method of superposition. So the first thing we'll do is to separate the cases. So how do we basically start this division process? So we'll say, okay, first we'll start with our simple supported, right? So we'll say for beam DF, right, for the simple supported portion, let's consider all of the load cases from basically the adjacent beams and the direct loading on the beam itself. So the first one we can see is this basically distributed load of 20 kilonewton per meter, right? So as we can see, so this is the first case. Another case would be, that is obvious, is basically this 20 kilonewton load on the, which is basically in the middle of this portion. The next one is 140 kilonewton per kilonewton meter, a moment, a concentrated moment in the clockwise direction. Now you might think that, okay, there's really nothing on this like point F. However, if you consider this overhang, and basically because what we're doing is to basically find the loading on only the simple supported part, we can consider this portion, right, this portion as a moment on support F. So we can basically take the moment of this right overhang on support, basically about the support F, right? How could we find the value? So it's 10 multiplied by 8 plus 30 times 2, which is the load, multiplied by 1, right, which is the moment. So 30 times 2 times 1 will be 60, 10 times 8 will be 80. So 60 plus 80 is 140 kilonewton meter, right? We'll do exactly the same thing for the left portion, right, for the left overhang. So as you can see, for the left overhang, we can say 30 multiplied by 7 minus 100, right, because this is in the clockwise direction, but this one is in the counterclockwise direction. So in total, we'll have 210 minus 100, or 110 in the clockwise direction, right, or it's in the direction that this force is acting. Now, before proceeding to the cantilever portion, one question you might ask is, why are we drawing this portion? Aren't we only finding the method of, basically, aren't we only finding the simple supported portion? And the answer is, you're correct, but we're finding this portion to find the rotation and see how the beam deflects in this portion. And when we are finding the deflection at point A and C, you will clearly see why we drew this part, right? And mainly because we are finding the deflection and rotation at point A and C, right? And because, for example, if we wanted to find the deflection at H or G, I would also draw this right side, right? I would also draw this right side, okay? And when we are drawing the elastic curves for each curve, you'll understand much better. So for now, just draw them like that, okay? Now, let's move to cantilever portion. So we'll have two other cases for the left cantilever, and the reason is we want to find our deflection and rotation at point A, and we want to find our deflection and rotation at point C. And again, another question might be, but didn't we already find the effect of the left overhang and even also the right overhang on the supports? And the answer is yes, we did find, but the thing is, that was for the simply supported portion, right? We found the effect on the simply supported portion, right? On this portion, on portion DF, right? But there is direct load on this portion AD, right? There is a direct load. That's why we are basically dividing it into two other load cases. We have 100 kilonewton meter and 30 kilonewton. Another question might be that why are we considering like this right side? And the reason is we are not interested in the deflection and rotation on the right side directly, right? So if you wanted to find the rotation and deflection again at this point G or H or any point here, we would actually have to draw this portion as well, right? With the method of superposition, we had to divide the load cases to a distributed load and a point load. But in this case, we don't need that. So we only, these two will be sufficient for our question. Although we could do these parts well, but they will not be used. So now let's start with the elastic curves and how they're going to look like. For the first two cases, it's pretty clear. So when we have a loading, symmetric loading on the simply supported portion, it's going to deflect like this. For this one, it's going to deflect like this. Now, the very important part I want you to take away from this elastic curves is the linear portion. Because, and you see, like, this is why I have drawn this portion, right? Because there is no load beyond point D, right? There is no load beyond point D. So at this portion AD, there's no load. So it means that whatever the slope or rotation is here, right? Whatever the value is, it's just going to continue to be like that, right? Just continues to be like that, right? Just and you can see this like if you have like, you can experiment with a ruler, right? You can basically bend this and have a support here, and you will see that, okay, there's no effect really on this portion, right? On this portion, there's no effect. So you can visually experiment and see like what this means. But because there's no loading, it's just going to, because there's no load, right? So it's just going to deflect, continued rotation, right? Just rotation is continued like this. Same thing for this. Now, for the third case, however, it's again really good. These elastic curves are really visual. So when I'm basically bending the beam like this, right? Bending, this is in the clockwise direction. I will have basically compression at the bottom and tension at the top, right? This is basically what we can imagine. So that's why our elastic curve looks something like this again, right? Looks something like this and then goes linear. And another question might be that why is it like maximum here, right? Near to the support. And the reason is our concentrated moment is acting at the support. So that's why the effect in terms of deflection will be much higher where it's basically nearer or closer to the support, right? That's the reason. Same thing is going to apply to case 4, right? Fourth case. So we have 110 kilonewton meter here, and we are again rotating. We have basically a concentrated moment of 110 kilonewton meter, which is in the clockwise direction. And so if we basically rotate the beam like this, we will see something like that. Okay, in this case, actually, our beam is under compression on the top and tension at the bottom. Now, very important point and part here for the cantilever portion. So when this 100 kilonewton meter moment is applied, the cantilever portion, okay, deflects like this until point C. And beyond this point C, because there's no additional load, it just goes linear, right? Same for this case, right? Same for this case. It's going to deflect like that and then continue linear after this point, right? After this point, it continues to be linear. So you see, like, this linearity portion that we are discussing is going to be the main and most challenging part in finding the deflection values using the method of superposition. Because otherwise, when you want to find deflections, it's clear, right? You can get the values from your tables and just find it at like in the middle here and the middle here, as you'll see for when we're finding it for point E, right? So these are very important to consider. Now, so we can just name these cases as 1, 2, 3, 4, 5, 6 to make it easier for us. And then now start with the deflection for point E, right? This is very important. Now, Let's start with point E because, it's basically easier. So we'll use 1, 2, 3, 4. We will not use the cases 5 and 6. And the reason is we are not interested in the cantilever, right? Point E is the midpoint of DF, right? Midpoint of DF, which is at this point, right? This point, this point. So we're not interested in the cantilever portion itself, right? We are interested in the effect of the cantilever portion, which we calculated here and here, but we are not, it's not under direct loading for the cantilever portion. So cases 1, 2, 3, and 4 will suffice. Now, what deflection are we evaluating? So this is the deflection at point E, and we have the rotation at point E. Deflection at point E for case 2, and rotation, right? Again, as you see, what is rotation? Rotation is the slope, right? And what is the slope? Intuitively, we can just say 0, right? Because it's symmetric and it's in the middle, it's maximum deflection, so 0 rotation. Same here, maximum deflection, 0 rotation. Now for case 3, we have deflection like that, okay? And as you can see, it's not maximum, right? And that's the importance of drawing the elastic curve. We have like a really comprehensive idea of what the sign of our rotation and deflection values are going to be like, right? It's going to be positive, negative, upward, downward, clockwise, counterclockwise. In this case, we will have an upward deflection. What about the rotation? So again, we see the importance of having the elastic curve, right? Otherwise, you could have drawn it like this, right? And the rotation, you would say, okay, it looks like it's 0, but in reality, it's not, right? And the reason is we have a 140 kN moment at the right side. So the maximum or peak value will be near or closer to this support F, right? And the same thing for case 4, right? We have a deflection here and we have a rotation. Now let's start finding our values for case 1. So for case 1, you can see from the table, you can go to your simply supported distributed load. You will see this formula and you can basically plug in your values. 5 times the distributed load, 20 kilonewton per meter, multiplied by basically your length of that portion, which is 15 meter. You can see it from here. Divide by 384 EI, right? So from here you will get this value. Now, from your table you can see maybe it's negative, maybe it's positive. My advice to you is just to forget about positive and negative, right? The reason is that's why we actually draw the elastic curve, right? That's why we have this. So we can clearly see if it's negative, if it's downward, is it upward, the rotation, is it clockwise, counterclockwise. So from here we can, simply see this is the normal shape of our beam and it's deflecting downward, right? It's going downward. So you can just, draw a, downward arrow like this, okay? Now let's move to rotation. Rotation is pretty clear, right? As we mentioned, it's the rotation in the middle is 0. Why? Because we have maximum deflection basically, right? Everything is symmetric. We'll have 0 rotation here. Now we'll move to the second case. For the second case, we have this formula, right? So you will basically go to your table, 20 kilonewton point load for a simple supported beam, and you will see this basically value, PL cubed over 48 EI. And you will put just 20 kilonewton times the 15, which is the length of the beam, and divide by 40. Again, like we were talking about only the simple supported, right? That's why we're choosing 15 meter, right? And your cases in the table also like are only, so you don't see this portion, right? You don't see this portion, right? And again, like this is only for understanding, and you will see why I've drawn this, right? So this is the value you'll get, and again, as you can see, the deflection is downward. So you'll just, see downward deflection. And rotation again will be 0. Now, for case 3, it can get a little bit complicated. So we want to find the deflection at midpoint. In some of the books, you can find the value directly for the midpoint, right? So in your tables, you will have the deflection value for maximum, which is at this point. And you will also find the value basically for the center of the beam, right? So both two values are provided. We're interested in the center, right? Not max. As we know, the center is not equivalent to the max for moment, right? For this more concentrated moment. So in this case, when we have the value, we'll just use it, right? ml squared over 16 EI. So this is the value you're going to find in your tables. So it's 140 multiplied by 15 squared divided by 16. You will get this value, and this is going to be again an upward deflection. Upward. You see, the deflection is upward. And if you cannot find, you will probably find this formula. However, in some of the books, I've seen that they don't have the center value. They only have the maximum. In this case, you can basically use the general deflection equation, and just for the x value, you can put like the half the value, half of L, which is in this case 15/2 or 7.5 meter, and find your deflection damage. So both of them will give you the same result, but obviously if you have like this option, the center option, basically the deflection in the center of the beam, just use this formula and find it. However, in terms of rotation, you cannot really find any value directly for rotation from your tables, right? So we are interested in this point. However, in your table, you don't have the theta value, right? So now this is when we need our basically general equation for deflection. Now, very important concept. Our rotation is basically the first derivative of our deflection curve or elastic curve. Why? It's basically, so what is this equation? So this equation is the equation for this curve, right? It is the equation for this curve. With basically the bottom line is this, the beam normal basically line. So, from calculus, from the courses that we have taken, we know that what is the slope? We know from our basically strength of material course that, okay, the slope is basically our rotation, right? Or slope or rotation or theta is basically the same thing, right? This theta. Now in calculus, we know that, okay, so if this is my curve, if I basically find the derivative of this, with respect to x, I'm basically going to find my slope, right? And that's it, right? So I will basically just, this is the value this is the equation you can find for moment case, right? Moment case. And you will see that theta E3 is going to be this. Just, take the derivative of this one. By the way, you will probably see that x is outside, right? I just multiplied in, so that it's easier to take the derivative. But you'll probably see in your case like mx multiplied by L squared minus x squared. This is the same thing, right? I just multiplied the x inside. So just to take the derivative of this side, because this side is basically, so this portion m over 6 EIL is constant, so it is independent of x. So you'll just take the derivative of this one. This will be L squared minus 3x squared, as you can see here, and just plug back in your 7.5 meter. Why? Because we are finding it in the center. So just 7.5 here, and you will see the final value. And now, very important, is this clockwise or counterclockwise? As you can see, it's this way, the slope. So if this is our normal, and this is our sloped or deflected shape, our deflection is going to be counterclockwise, right? So it's moving in the upper direction, right? It's moving in this direction. So that's why it's counterclockwise. Now, we're basically going to do the same thing for case 4, right? In case 4, we have, you can see again, like the same equation applies because we have the same moment, and ml squared over 16 EI, 110, which is our constant moment value. 15 squared over 16 EI is going to be this value, and this value is downward. Why? We see it from the elastic curve, right? And again, just don't worry about the signs from your book, okay? Obviously, if you feel comfortable with like using the signs and you can remember them, just you can use them for sure, right? But when we are using elastic curves, it's just more comprehensive. We can understand, we can see it with our own eyes, that if it's positive or if it's negative. Now we can move to rotation. For rotation, we're basically doing the same thing, right? So just use this equation, right? Just use this equation and plug back in again this 7.5 meter for x, and basically we're using this equation, right? So instead of m here, we use 140, just use 110, right? Because the same equation applies. Now we'll use this one. Now we'll see this value. Now, is this clockwise or counterclockwise? Again, as you can see, this value is counterclockwise as well, right? And the reason is basically whatever you see like in this direction, it will be counterclockwise. This direction, it will be clockwise, right? This line, whatever you see, it's counterclockwise. If it's like difficult to imagine, obviously you can see that this is, again, like deflecting in the counterclockwise way. So this is your normal curve, and this is your deflected curve. And you can see that it's moving like downward like this, right? This arrow, like this. So that's why it's counterclockwise, right? So counterclockwise, this way. Now, the only thing, so now the principle of superposition applies, right? So just add these together and obviously take into account the effect of basically sign, right? So it's downward, downward, downward. So add all of them together and minus this portion, right? So you will see the value here, basically this value plus this value plus this value minus this value. You will see this value, of course, in the down direction, right? Downward direction. And theta, same. So in this case, we only have 2 counterclockwise rotations, so you will just end up with this value. So this is for point E. Now we can move to our other deflections that might be a little more complicated. Now, for deflection and rotation for point A. Let's see again, like let's assess where our deflection is. So this is our point A, right? And for case A, we have, for case 1, we have this type of deflection. But as you remember, this is the main reason I draw this line, right? So as we know, this is not a curve. This portion is not a curve, right? This is the line, right? This is a line. So because this is a line, we're going to use the rotation value as you will see later. But as you can see, okay, so this is point A and this is our deflection here, and the rotation will be this. And as you can think, like this is the rotation here. But as we know, this is a line. So what does it mean? It means that our rotation here or slope here is the same as it is in point D, right? So this rotation and this rotation are the same. And we are going to use that in our calculation. Now for the second case, we'll see this is the deflection and rotation. So these are very similar to each other, right? So deflection and rotation for the fourth case. Now, this is what I mentioned here, right? Theta D1, this is very, very important. So if we find our theta D1, basically our question is solved for case 1, right? Why? From this triangle that you see, from geometry, because this is a triangle, as we know, right? As I said, like this is a line, right? This is a line, right? Because there's no load here, so this is going linear. And this is our normal, basically you can see the triangle here. So you can see that for our slope equation, we can say that, okay, this deflection divided by this AD portion is tangent, right? Tangent is equal to this value divided by this value, right? So, or the deflection divided by the length of AD, which is in this case 9 meters, right? Now, if I know that, I will say that, okay, then my deflection is equal to my tangent theta D1 multiplied by this portion AD, right? The length of AD, which is what you see here, right? Theta D1 times the length of AD, right? From triangle equation. So basically just basic geometry. Now, you might think, okay, this is tangent, right? This is tangent, why did I use theta D1? And the reason is in our assumption when we are basically deriving the equation for this basically deflection based on elastic beam theory, we're considering that we were basically simplifying our equation, and we are saying that our deflections and rotation values are very, very small. So because they are very, very small, we know that from calculus that our tangent function and our linear y equals x function, so y equals tangent x and y equals x function, are equivalent around 0. So we'll say, you know what, just, forget about tangent theta d1 because they're equivalent around 0, and we know it's very, very small. Just use theta d1 instead of tan theta d1. However, if you use tan theta d1, it's pretty much the same thing, but, why use that? We already assumed it in our derivation for the theory. Now, so we'll just basically say theta d1 multiplied by AD, which is the length, we'll end up with this, value. And again, where can we find this formula? Just go to the table for your simply supported, right? Find theta d1, which means you find the rotation at this point. So go to simply supported case, uniform load, and find this rotation. You'll see this value, okay? And again, forget about negative and positive. Multiplied by this length, right? As we derive, right? This is just simple geometry, right? Now, our deflection will be this value, right? So just basically substitute the values, 20 kilonewton per meter times L cubed, which in this case is 15 to the power of 3, divided by 24, multiplied by 9, which is the length here. AD length, you can see it from the bottom here. Now, we'll end up with this value. Is it positive or negative? Obviously, it is upward, right? Again, there's no positive and negative here, so it's just, upward or downward. In this case, it's upward. Now, what about the rotation? The rotation is basically here, right? That's it. So this is our rotation, right? Why? Because, as we mentioned, this is linear. So because it's linear, the rotation here is the same as the rotation here. So it's just equal to theta A1 is equal to theta D1 is equal to this value that we found, right? The rotation. So just write it again and find the value. And is it clockwise or counterclockwise? It's going to be clockwise. Why? Because if this is you can see, right? So this is clockwise, right? So this is your normal curve. This is your deflected curve. This is basically deflecting in the clockwise direction, right? Now let's move to the second case. For the second case, you can see this, again, this value. You see, like, the process is very, very similar, right? Again, what is our deflection here? Our deflection is this value, right? Multiplied by this length, right? As you can see, theta d2 multiplied by AD, or the length that we have, okay? Now, what is AD again? It's 9 meters, and you can find this value from your table for a simple supported case when you have a concentrated load and you want to find your rotation here. Again, as you can see, like, this rotation and this rotation are the same, right? It's the same point, so they have the same rotation. And you just, again, like, substitute back the values, 20 kilonewton, and you can find the deflection. Again, this is upward as well. Now, let's move to our case for rotation. So the rotation, again, will be the same as here, right? So we have the rotation here. And this rotation value will be the same as the one that we calculate, right? So this is the calculation we had, right? So this is the value. Theta d2, theta d2, theta d2. Just, again, put it back here, and you'll get your value, which in this case is, again, clockwise. Why? Because this is your normal curve and this is your deflected curve, right? Deflected curve. So you can see that the deflection is in the clockwise direction, right? Clockwise, right? Clockwise. Now, for the third case, we have, again, theta d3, right? Again, what is this value deflection? It's this value, theta d3 multiplied by the remaining length, AD, right? So again, we'll have this theta d3 multiplied by the length of AD. Now you will get, again, this value from your table, right? Now this is very important. So you have two values for rotation. You have, like, one of them at this side, one of them at this side. What we are interested in is this one. And what does this one mean? It means that you have applied your moment on one side and you want your rotation on the other side. Okay, that's very important. You have another case here, which is ml over 3ei, right? But, like, just don't confuse, like, these cases. These are, like, basically one of them is half of the other. So if you want to find the rotation at the location where you are applying the moment, which is at this point, that's ml over 3ei. However, if you want to find your rotation at the location opposite to where you applied your moment, that's ml over 6ei, okay? So pay attention to that. Again, and again, just forget about the sign, right? And we just plug in the values. We have 140 kilonewton meter, which is our moment here, times the length divided by 6ei, multiplied by the length of AD, which is going to be this value, and it is downward, right? As we can see, this is a downward deflection. For rotation, again, like you see, like the theta d3. When we are finding theta d3, everything is practically done for rotation as well, right? Because as we know, the rotation at this point is the same as rotation at this point because it is linear. There's no load beyond point D for this case, right? For this case. Now, how about the sign of our rotation? it's going to be counterclockwise, as we can clearly see. So this is our normal beam, basically normal condition of the beam, and this is the deflected condition. As you can see, it's deflecting basically in the counterclockwise direction, which is what we have here. For case 4, again, we have theta d4. Deflection is basically equal to this, basically the length that we have multiplied by the rotation, right? The rotation theta d4. And again, if you, as I mentioned this, like this is ml over 3i. Why? Because we are applying the moment here and we want the rotation at the same point. That's why the rotation is ml over 3i. And again, if you have the table in front of you, this makes much more sense to you when what I'm talking about. And as you can see, so this will be our value. Just substitute the value, 110 for the moment, length is 15. And again, like when we're talking about length for the whole, like for all of these 4 cases, we're talking about the length of simply supported case, right? Whatever you see like in your table, right? It's very important. And as you can see, the deflection is again upward, right? Upward deflection, which is clear from the figure. For rotation, again, we can see that it's going to be the same as this one. It's a theta d4, right? Which we found already here. So just plug in the value against, and you can see that this is the value, and the sign is again this one. Why is that the sign? Because as you can see, it's rotating basically in the clockwise direction, right? Clockwise direction. Now, the question might be, is this enough? So is that it? As we did for point E for the deflection in midpoint? And the answer is no, right? We have a cantilever portion, as we discussed before. We have a direct loading. We have direct loading, 2 additional cases for the cantilever portion. Why? Because we're finding it at point A, right? So we found the effect of the simply supported portion, the adjacent portion, right? But the portion, like the AD itself, is remaining. So we have to account for that effect as well. So we move to our basically our deflection for the cantilever portion alone. So case 5, we have this case, if you remember, right? So we have a curve here and we have a linear portion here, right? Now, what is our deflection? We have this portion and this portion, and you'll see why I'm dividing them like that. And again, for this one, you have this portion and that portion, right? Now, why am I dividing them like that? The main reason is that I can say that this case is, let me just show you what I mean. I can say, okay, I can divide this case into 2 cases. I can say I have this portion, right? I have basically this portion, I can find it from my table. I have a cantilever portion, and the moment is applied at the end, and this is going to be my value. So this is my rotation, my deflection right here. Now, what about this portion? As I discussed again like before, right? This principle of linearity when you have no loading. As you see, beyond this point C, you have no loading. So the rotation or slope will remain the same. Because it is going to be the same, basically this shape that you see here is a triangle. So what I'll do, I will just use geometry, right? I will just use geometry here, okay? So here's the shape, okay? So I just extract. So that's why I'm dividing this to 2 shapes, right? Two portions, like 2 segments. Now, for the first part, as you can already see, I get that the delta A51, which is this portion, is just a deflection that you get from this case, right? That's just the case that you get from this case. If you open your tables, you will see that the rotation at the end, the deflection at the end is this value, ml squared over 2ei. Just substitute back the values, and you will see you will get this value, and the deflection is downward, right? The downward deflection, as you can clearly see from here. Now, for this portion, however, is again like what we discussed. If we find the rotation here at this point, we can basically say this value is this value multiplied by this value. So 6 meters multiplied by theta c5 is going to be our deflection here, right? So it's going to be, as I mentioned, theta c5 multiplied by the length of AC, right? Theta c5 multiplied by the length of AC. again, if you go to your table, you will see that ml over EI is your rotation value, right? For which case? For the deflection case you have here. And why am I using that value? As I mentioned, the rotation, I'm basically looking for this rotation, right? Theta C5. Where is this rotation? Point C. So if I find my rotation from this case, right, from this case, at this point, at the end, which you have the value for, which is ml over EI, I can basically solve this question. So I'll say ml over EI multiplied by the length of AC, right, length of AC. And you can just substitute the value. You will see 100 times 3 divided by EI times 6. I understand this might be a little bit complicated to understand, just, take your time. It is not the easiest concept, okay? So, but this is basically the ultimate value that you're going to find. This is the ultimate difficulty for this type of question. So this is our value. So basically we found delta A15, A52, right? So just add the values together and you will get the total deflection from case 5, okay? For rotation, actually we have theta A5 is equal to theta C5. Why? What is the rotation we're looking for? Is this rotation, right? But as we know, this is linear. So it means that this rotation is the same as this rotation. So if I know theta C5, I know this one as well. So it's the same thing. However, do we know theta C5? Yes. From here, we know theta C5, right? We already used it in calculation of our deflection, which is ml over EI. And what is this theta C5? It's basically, in this case, right, in the cantilever case, at the end of your beam, right? At the end, you have a theta value, which you can basically find in your table, right? The value is given as ml over EI, okay? So just, again, put the value back in, like 100 times 3 over EI, get your rotation. And is it counterclockwise or clockwise? You can simply see that it's deflecting this way, right? Deflecting this way, which is basically counterclockwise. Now, we move to case 6. It's basically exactly the same thing, right? Only with a different equation because we have a point load. Okay, so we're going to again have this portion, right, for this deflection, right, and for this deflection. And we will have another portion for this portion, okay, for this portion. Now, so basically it's the same thing, right? So you will get this value from your table, right? The deflection at the end for a case like this, right? And again, forget about positive and negative, right? We see what it looks like. It's going up. So deflection is upward for this portion. So this is the upward deflection here. You'll just plug in the value 30 times 7 to the power 3. Why is it 7? Because of the length of this, right? So because, as you can see, like this is 9 meters. It applies for the previous part as well. You have 9 meters, the whole length of this cantilever. However, I'm dividing my case. I'm saying that, okay, let's consider BD. Let's consider BD, right? And this length is 7 meters. And that's why I'm putting 7 meters here, right? Because this is my case, right? I divided my cases to this one and this one, okay? And this is an upward deflection. For the deflection of this part, again, it's a triangle, just this value multiplied by this value. You will see the result. And again, where do I get this theta B6? It's this theta B6, which means that the deflection, the rotation at point B. What is the rotation at point B? It's going to be coming from this case, right? From this case. So from this case, I can find the rotation at point B here, for which I know the formula, PL squared over 2EI. Again, you can see this from your table. And I will say, okay, this rotation value, as I know from here, multiplied by the length, I will end up with this, basically 30 times 7 squared. Again, why is it 7? Because this length is 7, right? I am finding the rotation here, right? Rotation here. 30 times 7 squared over 2EI multiplied by 2, which is the remaining length that I had here, right? So this is AC, and this is the rotation, which is dependent on this, right? You'll get your value, and it's upward deflection again. Just add the values, you will see the final value. For rotation, again, it's pretty clear from what we did before. The rotation is basically at this point is the same as at this point, which is theta B6. We already found theta B6 for at here, right here. So just, put back the, just rewrite this here, you will get 735. And in this case, we have a clockwise deflection, right? We have a clockwise. Why? Because as you can see from here, if this is our normal beam, it's deflecting like that, right? Deflecting like that, which is clockwise. Now, add all of the cases, 1, 2, 3, 4, 5, 6 together, considering the upward or downward, right? So for case 5, we have this value. For case 6, we have this value, right? For deflection, for example, you'll get this value in the upward direction. For theta, you will get this value in the clockwise direction, okay? Now that we have this, for point C, pretty much everything is done, right? So this was the most difficult part, probably, okay? So portion C, we have, again, like these load cases, case 1, case 2, case 3, and case 4. And what we'll do is just follow the same process that we did before. We'll see that, okay, this is point C, this is a deflection, we have the rotation. Deflection, rotation, deflection, rotation. Deflection again here, and rotation like that, okay? Again, we'll do 5 and 6 on the next page. But for now, let's start and see what we want to find. This is exactly the same thing that we did for case A. We have the rotation here, and if I just multiply the rotation by this length CD, I'll find my deflection, right? So my rotation multiplied by CD, or the length, is going to give me my deflection, right? And where does this come from? WL cubed over 24 EI. Again, for the simply supported case, right? Because I want rotation here, right? At point D. Just take your basically rotation value from your table, which is WL cubed over 24 EI. Multiplied by the length, you'll get your deflection that we have, okay? And this length is 3 meters. Why? Because it's all geometry, right? So as we mentioned, this is your triangle. This deflection is equal to this length multiplied by theta d1. And the proof is what I mentioned before. It's just a tangent, right? Tangent theta d1 is equal to this value over this value. So this value is equal to CD length multiplied by the tangent of theta d1. But because the value is really small, so instead of tan theta d1, we just use theta d1, okay? So we have theta d1 multiplied by CD because of that. And where did we get theta d1 again? It's WL cubed over 24 EI from the simple supported case for uniformly distributed load. And you can get your rotation at this point, right? At this point. So you will end up for deflection for this value, okay? And this is an upward deflection, as we can see. For rotation, it's pretty much the same thing we did before, theta d1. So the rotation at this point is the same as at this point. Why? Because this is linear, right? This is linear. And we just, put this back here, right? And this is it clockwise or counterclockwise? It is clearly clockwise, as we can see, right? This is the normal, this is deflected, so just clockwise. For the second case, again, we need this theta d2. And if you remember, actually, we calculated all of these theta d1, d2, d3, d4 before, right? But we're doing it again, just to, solidify the understanding. So theta d2, again, like this, theta d2 multiplied by the CD is going to be your deflection, okay? So, and where do we get this value? Again, just take this simple supported case, take the rotation at this point, which is PL squared over 16 EI from your tables, and multiply by the CD length, that remaining length that you have here, CD, okay? And you'll get this value. This is an upward deflection again for rotation. We're exactly doing the same thing, okay? And this is again clockwise. For the third case, we have theta d3. Again, we did all of these before, but again, as you can see, this is, I know that the deflection is my rotation, or theta d3 multiplied by CD, right, from geometry. Again, where did I get theta d3? Just go to this case, right? Just go to simply supported, moment applied, okay? And you'll get ML over 6EI, as I mentioned before, right? Again, as you see, I'm finding the rotation opposite to the side that I applied the moment, right? So that's why it's ML over 6EI, not ML over 3EI, okay? Multiplied by CD, and you get your values again. There's a downward deflection, obviously, right? It's going down. And for rotation again, theta d3, right? This value, right? Just put it back there. And why is it theta d3 again? Because at this point, the rotation is the same as this point, right? Why? Because this is linear, okay? Now, for the last one, it's basically, again, the same as the third one, right? With the only difference that this is ml over 3i. Why? Because I'm applying my moment at the side that I want to find my deflection, my rotation. So basically, I'm using ml over 3i instead of ml over 6i. And again, I will do the same thing. In this case, I'll only just put 110, my value is 110. And, this is going to be an upward deflection, as we can clearly see. Now, for rotation, again, it's theta c4 is equal to theta d4, same explanation, and 550 over ei. It's going to be clockwise, and the reason is, if this is your normal beam, this is your deflected beam, it's deflecting basically in the clockwise direction, okay? Now, next, we're going to cover the cantilever portion. For the cantilever portion, it's basically pretty much the same. However, it can be a little complicated because I'm finding, for this case, point C at some point, which is not the middle, not really, so, it's just a random point probably, right? So let's start again, like you see, this is the deflection, this is the rotation, this is the deflection here, and this is the rotation, right? Now, I will say that, okay, this portion is pretty easy, right? I will say that, okay, I have a moment applied here. I have a cantilever portion. So for this 3 meter length, right, that I have, just find my deflection, right? I have this case in my table, right? For the cantilever portion, where moment is applied, the deflection and rotation at the end, okay? So for deflection, you will get ml squared over 2ei. It's 100 times 3 squared over 2ei, right? 3 is the length of this portion, right? And again, like, this is very important to understand, right? So the C, why am I taking CD? Why am I not taking this portion AD, right? The reason is, I'm only using this portion. So what we are doing here is just to find the deflection at this point, right? At this point, right? And that's why we're taking this portion, okay? Now, as I mentioned, ml squared over 2ei, we're going to end up with this value. And the value is downward, as we can obviously see from our curve, okay? For theta c, it's going to be this value, right? And if you remember, we already found this value, right? And although, again, like, we can see our, we can find our value, right? This is basically the same as we found before, but the formula is ml over ei, right? When you have a case like this, your rotation at this point, right, is ml over ei, which we did actually in the previous, for point A, we found theta c5 already. So, or basically, yeah, theta c5 we already found it, okay? So was going to be counterclockwise, okay? Counterclockwise. Now, for the second case, if you want to find deflection, we want to find deflection here. However, our load case is here, right? As you can see, I'm just eliminating the left part, like left from B, right? AB, I'm eliminating that. Why? Because I really don't need that. I'm not interested in that. It's just linear. After this portion, I don't really care about it. I'm trying to find, my rotation and deflection at point C, okay? So I have this case. How can I find my deflection at this point? From our tables, we can't find anything, right? We only have our deflection at this point. So what we can do is just use a general equation for deflection, which is this equation. So what we'll do is just use 3 meter for our length, right? 3 meter from support. So use x as 3. Just substitute everything back in. L is 7, right? L is 7. Why? Because load is applied here, and this is my load case, so this is 7 meter. Divided by 6ei, as we have here, just get your final value, and it's going to be an upward deflection, right? As we can see here, okay? It's upward. For rotation, what I'm going to do is just take the derivative of this curve, right? As I mentioned, what is this? This is just the elastic curve equation for this curve. So I'll just take the derivative, I'll find the slope, which is here, right? I'll take the derivative of this one, is going to be 6lx minus 3x squared, right? As you can see here, and just plug back in 3 meters for x, and that's it. So this is going to be our value. And is it clockwise or counterclockwise? It's going to be actually clockwise, right? Why? Because this is our normal beam and this is our deflection here at this point, right? It's deflecting like this upward direction, which is basically clockwise, okay? And now the last thing we have to do is just add all the cases together, case 1, 2, 3, 4, 5, 6, considering the negative and positive, or basically downward and upward and clockwise and counterclockwise, and we'll end up with this value, which is in the upward direction for theta c. It is the value that you see in the basically clockwise direction, okay? And that's basically done for this question. So if you enjoyed the video, please like and comment down below and subscribe for more content about problem solving in structural engineering. And I'll see you next time.